Cool. So he was asking about homework question 5. Is that what you were here for as well? Cool.
Yeah.
So everybody's on the same page. Let me bring it up. So this, right?
Yeah.
Okay. Is everybody on the same page as to the definition of it?
I think so.
Yeah, I understand after the answer on Piazza for sure.
Oh, I didn't see the answer on Piazza. I don't call Piazza.
I think like what it's saying is that there's some
It's hard to keep up.
natural integer or some natural number k, and for r, m, and n means that there's some k between m and n, and we pick k words out of r and concatenate them to make a string.
Yeah, that's right.
Okay.
Right.
Okay, so we want to prove that this doesn't, that this still only describes like regular languages, right?
Mm-hmm.
That we can take a regular language, apply, what do they call it, concatenation ranges, and that if, wait, let's see, so it would be if LR is a regular language, then this should be a regular language, right? That's
so
what we're trying to prove.
RMN is part of R? Is that what that's saying? Or?
So LR is regular implies LR bracket MN is also regular.
Right.
Okay. Okay, that's its own language.
Right. Because if I have just some language that's only just undecidable, for example, if I just put the whole thing from the then of course concatenation ranges of the whole thing problem no longer makes any sense. These are always just regular languages, but for the purpose of the proof, you're really just proving, right, that if this is regular, this is regular for any m and n.
So I know Aritra said, is that how you say his name?
I'm not sure.
He said to use the properties like the operators that we've defined for regular expressions in our proof as opposed to the NFA method which we used in class. But I still think the NFA is kind of useful to get an intuition for this problem.
I would do this. This is okay. First of all, it says show. Whenever I see show, I don't think prove. I think you show a deep understanding of the truth of it. You don't prove it necessarily for in every tiny little way. But you show that without a doubt you understand how to do this and your method works. So I would do this with NFA.
So the idea, right, is that you have R and you can repeat R anywhere between M and N times, where N is larger.
Yes, but you also don't know where you're repeating it, right? Because you don't know where you're making these cuts. You're trying to decide, when you get something into your DFA, it's just a string, right? And you're trying to decide if it's in the language, right? That's how these NFAs and DFAs are working. So when I get this string in, another way to phrase this, right, is can I chop this into k pieces such that each piece is in the language, right?
Right.
And so the machine kind of
Yeah, my intuition would be have the big adder machine, and within it you're going to have M as the lower bound. So you're going to have M machines that are all copies of M sub R, which is just a regular expression. And you have to pass through all of those. So you're going to go to the start state, and then you pass through it once, and then you get an epsilon move to the next one. And you do that M times.
Notice it's actually more like M minus 1 machines you have to pass through, because once you're at the mth machine, you can start accepting, right? Because it's M less than or equal to.
Okay.
Yeah. These are there's so many small trip-ups and stuff like this, right?
Alright.
Why not k, though?
Well, so k can be between M and M. So you also have a maximum is the point, right? So you have your minimum number you have to go through, and then you have a maximum. So you have a bunch of optional machines. And the optional machines are ones where you could either so you're at the previous machine, you could either do an epsilon move all the way to the end, or you could do an epsilon move to another machine, go through that one.
Okay.
So all of those have to have epsilon moves to some final state for the whole big machine.
But then doesn't that mean that you have n minus 1, but only after M can you start making those epsilon moves to the final one?
Only after, right, exactly. After you've gone through M of them, or M minus 1 of them, then you could start going to the final state.
Yeah.
And then or you can go to one more machine, do one more.
Yeah, exactly.
Or you could go to one
up
more.
To N.
Up to N, right.
Yeah.
So I like pictures. I don't know about you guys. let's just try and visualize this as well as just talking about it. I should also draw it bigger because the camera has terrible zoom. Super fancy building, crappy cameras. Okay, so we got our start state, right?
Mm-hmm.
We've got all these normal states that don't matter that much. We've got these accepting states, okay? So if we take, so this is accepting, so let's say, okay? So this is like where our starting point,
Okay,
right?
so that's your M sub.
Yeah. So now we want to build the rest of the board is going to be a machine that accepts,
The concatenation.
Yeah.
range.
So those are just kind of like a black box for all we care, right?
Yeah, like you don't have to look inside.
Right, exactly. Yeah. I mean, you say comment on stuff that's inside, kind of tangentially, but you don't like actually look at exactly what's going on in here. Why did I write a D? That's not how you spell. Want NFA accepting L of R M N. Yeah, video is actually probably almost most useful to the people who come, because then like you remember everything that happened here, but if you like forget a single piece, you can just like go back and be like, what is he saying here? For like not forgetting corner cases and stuff. Other people really just kind of do have to watch the whole thing to understand most of what's going on. Okay, so want NFA accepting that. This is what we want, right? Okay, so just for sake of example, let's say M is greater than 1. Okay, so should these stay accepting states if M is greater than 1? So let me put.
If this is the first copy, then no. Well, yes. For
Yeah. This is our real start state. We're keeping it. Let's keep this as our start state for now. And so this is our first copy of M. So
it should be an accepting state for like the inner machine, but not for the outer one.
Yeah.
yes. How do we indicate that it's an accepting state for the inner machine, but not for the outer one?
By not having an epsilon move to the final state of the outer machine. Well, that's how he's been doing it in class.
Yeah.
So how I would do this at least is, okay, I want to just chain a bunch of, yeah, I'm not at lectures, so I see like what he puts up, but in his lecture notes, but I'm not always 100% sure of how he talks about things. I should write these S's bigger because they're freaking minuscule. So I want to get to my next start state, right? Because I want to be chaining things together. I don't want to accept here. So what I'm going to do is cross these states out and replace them with, like, I'm basically just going to make them not accept states. I'm going to keep them for the most part. I'm going to make them not accept states.
Okay.
And I don't know if where I am in, like, my computation, if this is actually where I want to stop, right? Just because this substring that just because I've found a substring that brings me to an accept state in the first machine, doesn't mean that's where I'm making the cut.
Yeah.
Right? So what I really want to do now, actually, is make an epsilon move.
Yeah. To the next start state.
To the next start state. Right? Because now, this satisfies everything, right? Like, now that it's been in an accept state, maybe we make our cut here.
Or you could stay in.
Or maybe we stay in. But certainly we don't just accept, because in this case, M is strictly greater than 1. How many, and then this is just going to be doing its thing, and how many times do we do this? Let's say, let's say all these machines
So this is where, can you explain?
don't accept. So let's say these are the machines you were talking about, right? Those leading
I
machines.
see. So this is why you want M-1 that don't accept.
Yeah.
Okay. Yeah.
So we want
So the mth machine is
minus
going
1
to
copies that don't accept. This is the way I think about it. There are many ways to do these types of problems, I suspect. So
be. Yeah, I was going to ask you about like the purely, I guess, regex manipulation ones too. Although I think the machine is more intuitive.
yeah, I think the machine's more intuitive. I mean, I think what you could do is like, I'm sure you could use regular expressions to just, it might be easier in
He gave us
some
a bunch.
technical sense.
Based on like the operations he gave us in class, I think you can algebraically get there.
You definitely can.
But
Yeah, you basically are just like, oh, look, you can rebuild these using the symbols. So like if you're a guy who likes crunching formulas, I don't think though like moving formulas around actually gives you much intuition as to why this is true a lot of the time. It's probably a shorter proof or like shorter result.
Well, this is impossible to like put in LaTeX, so that's the first thing.
Well, you don't have to draw this though, right?
Yeah.
You can
Say this in words. I have
Yeah, yeah,
-1 nodding.
One thing I try to drill into people in discrete math is like, I was very clear. I was like, you can use words. You don't have to write equations, but be very careful. One, there's problems with both. Like doing all equations can like hide the intuition and be unintuitive, and you make mistakes because you've lost the intuition. So it's hard to tell if you've made a mistake with the equation because you don't have any intuition as to what's right or wrong, right? That's why you do. It's always good to do like sanity checks in math when you've like lost intuition as to why it works. Like you just try some examples and see if what comes out of like your formula makes sense. Like we call those sanity checks.
Okay.
But with the word one, the intuition is better. It's easier to miss like corner cases and stuff. So like being careful about things like n-1 copies except. It's easy to like intuit wrong and then like not see the mistake.
Yeah.
But for now, because I have this big board, I'm just going to be drawing a bunch of stuff. I'm going to do it this way for now.
So the mth machine is going to be the first one.
Make it smaller because I'm running out of room. We have epsilon transitions to it. Right, so this is the first one that has accepting states, right?
Yeah.
Okay. But M is just the, in fact, I can erase this bound now because I've said n-1 copies that don't accept.
Yeah, it doesn't have.
But if M is 1, then your first machine accepts. It basically is all. You don't
have 0 copies.
Yeah, you don't have this phase at all. Okay, so this machine's accepting if you can break it into M pieces, right? Like if you end in one of these accept states, the reason you're accepting is because you can break it in your string into M pieces, all of which are in LR, right?
Yeah.
But we can have more. You can break it into more pieces, right? So we need another kind of like set of machines.
Which is M plus N.
And what do I do when I'm at these accept states?
Or N minus.
So what do I do with these accept states? I definitely leave them accept states, but what else do I need?
You need an epsilon to the next one.
Exactly.
So you end up with N minus M plus 1 copy.
So this is, sorry, what was it?
N minus that, which is N minus M plus 1. Or N minus M quantity M minus 1.
Sorry. And oh my god, why do I keep saying this? N minus M
Plus 1 if you've already distributed the
plus 1. So that's, is that right? I'm going to do a sanity check now because once again, now I have an equation and I'm just going to like plug in random M and N and make sure this actually works. So like, let's say I have 1 and 1, then this is working because there should be one machine that accepts. It's basically the same machine, right?
Yeah.
Okay, so it looks good under, let's say 1 to 2. So then it's accepts if it's 2 minus. So then M would be 1. If N is 2, that's not great. It's backwards, right? Wait.
Isn't
N,
N-
oh no, N is always bigger.
Yeah.
Yeah, sorry. No, this is exactly.
No, but it still seems wrong.
It's
for
still
1
wrong,
to
though.
2.
So I think you add 1 to N, right? No, that doesn't change anything. What are we doing? So like, certainly if M equals 1, N equals 2, this is what I'm doing in my head where the sanity check failed, then this needs to equal, our little equation needs to equal 2, right?
Right. But so you have 0 copies that don't accept.
Yes.
And then you have 2 copies that accept.
Yeah.
So we want.
This should also be N minus 1, right? The next
We want
phase
N
after-
minus, N minus
Oh, N minus...
M minus 1,
Different.
which means N minus 0, which is 2. So N minus the quantity M minus 1 That's why.
Sorry, what was it? Oh yeah, it's wait.
If you do n and then subtract that on the left side,
Mm-hmm.
so we
Oh, and
we know we have two total machines, and none of them are on the left side because.
okay, yeah, that works.
But that ends up being.
That's
the
it.
That ends
minus
up
one
being
plus
M minus
one.
one. So I guess I'm just bad at arithmetic.
But I don't know that you are. I think there might be something wrong.
But that makes sense.
Oh, you know what? It's because I was doing.
2 minus 1 plus 1 is 2. Okay, yeah.
So it should be a minus sign there. We had a plus sign there before. That was our issue.
No, but once you distribute that negative on the outside of the parentheses, it becomes a plus if you get rid of the parentheses. You see how?
If you get rid of the parentheses. Oh, because it's minus one. Yeah.
Yeah, because it's a minus inside the parentheses.
I think I was just doing it in the wrong order. For some reason, I was like doing it backwards. Like I was doing this first for no reason.
Yeah, so that's equivalent to.
I'm just bad at PEMDAS.
So 2 minus.
It's too much Hebrew. I was reading like right to left. And okay. Yeah. So that works.
2 minus 1 plus 1, and we get 2 on the right, which works. Okay.
Cool. So that works.
So-
and then here. So okay. Once we have gone through, split it into n pieces, we're still accepting, right? If we've split it into n pieces.
Mm.
But after we've split it into n pieces, do we need machines after that, or
Wait, is that
We
the
just
nth
need-
machine?
no? I guess we're just good.
I
Right,
guess.
let's see.
So in the last copy, so like once you've accepted n minus 1 or whatever, however many you're going to accept. Yeah, once you've accepted n minus 1 machines, so you're in the last machine.
Yes. Do we need these?
If you keep processing characters and you reach a non-accepting state, then that last machine no longer accepts, so the
Right.
whole machine no longer accepts.
So do we need more epsilon states and more things?
No.
But I'm wondering how you jump from one of the initial ones to like the first one in that second group. How do you jump to the final state?
So okay, let me. So point to what state are we talking
So
about?
let's say you're in that one.
Yep.
So you're in the first machine that could be a final machine.
Mm-hmm.
Now you need to jump to
So the way he's been drawing them in class.
so each one is a final machine there.
Yeah,
Okay.
so he's saying like if you circle it, it's a final state for the whole like big
Okay.
machine.
Yes.
The way we've been drawing them in class is basically he draws like a smaller box, and that has its own start state and its own accepting states. Like he would leave the circles on those earlier ones, and then if he wants the whole machine to accept, then he draws a final state out for the
Yeah.
big machine, and he does an epsilon move over to it.
But this kind of makes
Okay.
more sense because from
Yeah.
like I was confused because like let's say in that first block there you have two options: you go to the next one or you go to the
Yeah.
end. But each of them need epsilon jumps,
Mhm.
and I don't know if you can have two epsilon jumps from the same thing.
You can have as many epsilon jumps as you
Okay,
want.
never mind then.
I like the intuition here personally. I think like both ways are perfectly valid ways of representing it. In my case, I need a bunch of different accepting states, and in his case, he only needs one, which is kind of nice.
Mm-hmm.
But I like, what was it? I like the clarity this offers in some sense of like for this particular example of just like every machine. You're just making copies of the old machine. You're barely doing anything else, right? You're adding epsilon transitions from accept states to the start state of the next copy, and you're keeping them as actual final states for the total machine when they're in this portion, and you're doing that.
Yeah, it's very intuitive. I think stating it formally is just the like tricky part
Yeah.
where you can miss an edge case. Because like one thing that we didn't necessarily account for here is if m is 0,
Mhm.
and then we're saying we have m minus 1 copies that don't accept. We're saying we have negative 1 copies that don't
Mhm.
accept, which is kind of not intuitive.
Wait, so
If the lower bound is 0, so we can have nothing. We can just accept epsilon, like no expression, no regular expression.
You can just be like max m minus 1 0.
oh, I see. So if we're doing, that's a good corner case. So this is another example of these problems, like a lot of the trickiness just being in corner cases. So what is m pulled from?
It's in the brackets, like
So M and N is a
Concatenation.
member of little omega. What's little omega?
Oh,
Natural
okay. So we're
numbers.
assuming the positive natural numbers. Okay. So yeah, this is what confused me because I've only seen the naturals represented with like the N with the crazy letter.
I think I've probably seen
Li-
that in his
little
notes
omega-
before because I've TA'd with him before, but I've never seen it outside
Yeah,
of
it
students.
apparently can mean natural numbers, and I guess if you're defining natural numbers as starting at 1 and not 0, then you'll be safe.
Do we know how he's doing it in this course?
We don't, but I would think for if you're going to make this, like if you're going to do this proof about concatenation ranges, you would want to support 0. Because
I mean, it might. Well, natural. So I usually think of natural numbers as starting with 0, but other people think this is why I hate the natural numbers. So personally, I think natural numbers should always start at 0 for at the very minimum. The reason that Z plus exists, like you just write Z plus if you want to do one and greater. So like, why even bother?
Or even
having a natural numbers if you could just use Z plus.
I've even seen it done as like N sub 0 and N sub 1 or something.
Yeah.
I don't know.
Well, let's check this. Let's check this out. Do you think he says in these lecture notes?
No.
Ever?
I've never seen him
It's
use
the
it
only
regularly.
time he mentions the symbol.
But I think it has to include 0 because M can definitely be 0.
Yeah, exactly.
Wait, is he even consistent in his own notes? Let's go to his discrete math notes for a second. And see.
Like, if I were using this concatenation range notation, I would absolutely want to have the option for it to be 0.
Yeah.
Oh yeah, I agree. I have no idea what he's defining it as. So okay, here's his notes from this year. I don't think so. Winter. Winter 2018. That's what we want. Okay, so let's go to. I'm pretty sure he used N.
Yeah,
So I TA'd this last quarter.
Yeah.
Okay, but here's what it does. It tells us that his natural numbers
start
include
at
0. Even though
So-
he uses different symbols in discrete math for it, I'm going to take it as...
So then we definitely have this edge case.
So he just like said that in class, that the omega equals natural numbers?
No, he didn't say that.
And where do we know it from?
We know it
Somewhere
from
on
Piazza.
Piazza.
That's literally it. Like,
Dude, there's so many posts on Piazza, and I'm just like overwhelmed by the number of posts that hit there. It was even worse last quarter.
well, it's a lot of students, yeah.
Yeah.
Um,
No, I've realized when I go to them when I see the emails, but like Eritrea is like really on it. He's just like Eritrea and Stewart combined have been like answering them faster than I can view them. So shout out to the real heroes.
So like you suggested, we could say like maximum of n minus 1 and 0.
Yeah.
Or we could just like say if it's 0, then
If m equals
no
0,
copies that don't accept.
well, okay. So if m equals 0,
yeah. Just anything less than...
Then
and
you start with one of those.
then what does
Actually,
that
your start
imply?
state has to be an accept state.
I think that's it, right? There's
Yeah.
no other modification.
Well, you don't have any of these. And,
Yeah, I mean, you
and
don't
the
have any of
start
these,
state
yeah.
of the first machine.
You
has
could say
to
like
be-
min 0, of course, for this, because then so like 0 minus 1 minimum of 0 covers that, and then
Right.
these
Max.
don't exist. And you say if m equals 0, make your first state in here
A
an
start.
accept
Yeah.
state.
a final state. Sorry.
If it isn't already,
So
Yeah.
like if it is
that-
already, then it doesn't matter.
this is where I think like his notation has like a slight advantage. Where if you've defined a separate start state for the big machine
Yeah.
and a single final state, then you could just be like, all right.
Yeah, it's true. It's all a matter of just like
Yeah,
comfort and preference. If
Wouldn't that would actually be on like the far left one, right?
far left ones wouldn't even exist if m equals 0.
Okay, yeah.
Because we like make that min 0.
Yeah, that makes sense.
Yeah.
Um,
Sometimes these don't exist, which is weird. And these don't exist if
Yeah.
right, like this is the real start state if
Yeah.
oh, that's not how you do an R. That's too many things.
Would it be possible to go over kind of how we could do this without drawing like algebraic?
That.
Yes, we can do that. Let's see.
Yeah, like I thought about this first, and then I was like, okay, how can I translate this into?
Everybody good with this? There's a video of it, so you don't need to like.
Yeah.
You can just go back and it should be up in a couple hours. I'm gonna try and be posting them immediately after things. I don't do that much editing. actually kind of in part because it does make it harder to find the solutions. Like if you were here, then you're like, oh, I know he said this before this, and that's easy. But like, yeah, I want this to be advantageous for people who like logistically it's complicated to make it to office hours. But they still have to go through the effort of like hearing the same arguments and understanding it all, which is ideal. Yeah. Okay. So algebraically, it's a good question. I'll probably cut a bunch of middle portion here of the video because I'm gonna have to think about this for a moment. Because when I saw this question, often when I see questions, I just like think of one way to do it, and then I'm like, oh, cool, I'm done. But this is an interesting idea. How to do it algebraically.
So the first thing I noticed was that
Yeah, let's take your guys' suggestion. 'Cause I haven't thought about this yet.
was that you can basically partition this into a union of, so like he defines in the problem statement, he's like you have some k where k is greater than or equal to m and it's less than or equal to n, so it's in the range of m to n. And you could basically partition that regular expression, the range, into a union of specific k's. So you have m, m plus 1, dot, dot, dot.
Makes sense.
And then all you have to show, because we know that unions are, the regular languages are closed under union. You just have to show that each of those languages is a regular language. So you basically have, each one is going to be like r to the k.
You want to take a stab at it?
Sure.
You seem to have a very like well-formed idea of this, so. Like I agree with your intuition.
Very badly on so we'll see. I'm like not. This is helping me develop my rigor.
Yeah. Yeah, let's let me be a critiquer in this case rather than.
Feel free.
Yeah, honestly, that alone is like often a good reason to go to office hours, just like to tell the TA your answer so that they'll tell you if you've missed stuff. Okay, so what are we dealing with? We're dealing with, what is the hat over union? I'm not familiar with that.
This is just like a big union. Like I'm unioning all of these.
Yeah. Okay.
From
I see.
M to N.
Oh, it's an N. Yeah, sorry.
It's an N.
I was like thinking of it as like there is like a, I think, tech thing for like hats over, anyway.
That sounds
ignore
awful.
it.
Right, so I'm unioning from k equals M to N, and I'm saying the language of k is just going to be L of R. I'm exponentiating. Now, I don't know that did we define that?
Yeah. No, that's well defined. That's actually.
I think he does that in a previous lecture.
I mean, I think of it as well defined, but you're right, I should probably find it in one of his lectures, because really you should only use notation that he uses.
I think it was that.
Other people do it, like it's in other textbooks, but here, let's go to lectures. I was just staring at the sky from the camera view.
I think it's the third.
That sounds legit. I believe you. It's a closure property thing, right?
Yeah.
But
And actually, I think
I don't see it here, which is obnoxious.
I think it's actually the fourth one.
Is it the fourth one?
Yeah.
I just left the fourth.
Yeah.
Here. Let's see.
Yeah.
Power setting concatenation. Okay. This looks promising.
Delta.
No.
No, he has like exactly what you
that's not
wrote. I think.
He has it with star. So he has it with star.
That's the thing, is that star encompasses all of these, but
that's not.
But yeah, I know
What
it's
is
not like a very.
Where does he do all his proofs though? I don't know. Closure properties. Okay.
Because like, let's say that my restriction. Okay, is there actually a counterexample to this?
And
For
actually,
general-
I want to
for-
say I wrote this. I think I wrote this backwards. I think.
So this is, to be fair, this is true for this type of K. But like
in general, if K words
for like arbitrary sets of numbers K, this is not true, right?
especially if K were negative.
Even like leaving that aside, couldn't I just say, I could say that like K is the set of all primes or something, and DFAs can't handle that. So like it works because of the K you've chosen, but this is actually not generally true. Star is true, but it's true in your case. So we need a slightly different way to justify it algebraically, I think.
Okay.
Let me. We're talking about.
Yeah.
The problem.
This isn't necessary. Like, yeah,
This doesn't work.
you can.
This itself, I don't think works alone.
This
you
is
need
kind
some.
of going top down.
Mm-hmm. Yeah, for sure.
We can also go bottom up where we pick. So I also thought maybe a good way to do this would be by induction, but then your base case is kind of annoying because it's this M. So you can kind of show that
If you do induction, you're basically doing what I'm doing, right? Because then you have to talk about like, you basically do the thing we just did. We already solved it one way. We're just solving it another way.
Is the one way you just like you don't really need to build an automaton. It's just a combination of.
I built an automaton. That is the first way I did it. That's how I would have done it. Is I would have just built the automata. I don't think it's hard.
Okay, so I was just saying like I was being lazy in the
Yeah,
sense that I just need to do a sum, so I can like very simple by trivial induction I can show that the plus and the concatenation are extend to arbitrary regular languages. So like a plus b plus c is also a regular language.
Mm-hmm.
And by doing that, I just need s to the n plus s to the n plus 1 all the way to s to the
As union languages like he's doing here.
So
yes.
if you do
So-
induction, you get this very easily, right? That if this is regular, then the next one's regular because
Mhm.
you're just concatenating one more copy. But the base case where you have M is kind of annoying.
I don't think it's that bad because m is some finite value.
Yeah.
So what you can just say is like he was saying, where we know we're closed under concatenation for some finite number of strings.
So it's just like
And you know-
concatenating together.
Yeah.
M
M
minus
times.
n
Is there
regular
like
languages.
a big concatenation? I guess you could
I mean,
say-
you can just do it. Yeah, like literally m times.
And I
This
can say
first of all,
m
once
times.
again, this says show not prove, so I'm not gonna like say do a really obnoxious, unnecessarily detailed induction on this. Like, yeah.
So like this could be your whole induction basis and then inductive steps.
So that's the basis, and then LK is regular, RK plus 1.
You can just say LK concatenation with L of R.
Yep.
Is L of K plus 1.
Yep.
And then you're done.
Yeah, so you don't really have to build an automaton.
Yep. I like building the automaton. It's nice.
I just don't want to draw it.
Oh yeah, you don't have to draw it. I would never have drawn it like on the homework because drawing in tech is
So,
terrible.
Yeah.
But
I don't know if this is this is kind of like a crazy, like there's no reason to do this, but I thought it'd be kind of funny if you took like you do n equals n times plus r. So like this is just division algorithm, like you have some
Mhm.
divisor. Wait, I don't know. But basically, you have some m is smaller than n, so you have some number of copies of m plus you have a remainder. So
Mhm.
you can do some modular arithmetic, and then you could do strong induction and say that if I do this, if my k is bigger than m, and I divide it by m, and I have a remainder, then I can concatenate those.
sorry, I just want to check one thing. Oh, actually, this camera's more lenient than I thought. Okay, sorry. What were you saying?
So I was saying you can take k, which is big. So you have your base case, and then you can take a k that's bigger than m,
Mm-hmm.
and you can do the division algorithm. So you could say it contains however many copies of m plus some remainder, and all of these are smaller than k. And so by strong induction, you could get that that L of k is regular because it's a concatenation of like L of m. However many times concatenated with L of R and all of these are regular.
It's basically the same thing because like
It's
Yeah.
basically the same. But I just thought it was funny
yeah.
to like do it with strong induction obnoxiously.
So wait, M is your
It's the
first
lower
ones
bound.
that don't accept, right?
This might be a problem because like the remainder could be smaller than M, and you only did a base case of M.
wait,
But
I'm
you could
confused
start-
about the.
Yeah, I'm confused by
so-
this.
So I think you're getting confused here because this is like here in this case if you're just doing numbers, this is an integer. So
Yeah.
what you really need, can I see that for a sec? Like if this is if I call the remainder like R prime where that's the remainder, that's
Mhm.
R prime copies of like bold R, which is this guy's machine. Like okay, so the number will be like R prime, but what I'm saying is like you would need R
No, it should be
LR
R prime.
copies
It should
R
be
prime copies of LR.
right.
Yeah. Not one LR.
No, I didn't. I meant.
Oh, okay.
I meant R. Yeah, like.
So, like,
in
that
L
times
of R.
R
Yeah.
prime.
Okay.
Yeah. Sorry.
Oh, I see. Just
Yeah.
overloaded
Yeah.
notation.
Yeah.
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 Okay.
Sorry.
No,
I used
fine.
L of R.
Yeah, yeah.
R is
and
intuitive for remainder, but
Yeah,
like
it's also that R.
It confuses
Yeah.
them.
I definitely
Yeah.
think the normal induction is the
No, the
easier
normal
one. Yeah,
induction
Comes
is
in.
better. I just thought, yeah, it's kind of funny.
Okay, so we're just getting back to some of the cut, going back to some of the regular expression stuff and the shorter inductive way to prove to do problem 5, right? So, sorry, what were we saying?
Don't you need to? So like this concatenation range is how
Mhm.
we're expressing. We have some number of copies of R between M and N. And to do that as a regular expression, don't you kind of need to union regular expressions which have fixed numbers of copies of R?
So LR is regular, right?
Yes.
Which means that and I know if I concatenate two regular languages, then the result is regular, right?
Mhm.
So really just this line I guess I'll write it on the board. But.
And we also know if we concatenate two regular expressions, that you can like split it up.
Yes. So we have LR is this one's good, right? Check, regular. Which means LR is going to be regular because it's closed under concatenation, and it equals the regular language LRR, right?
Yeah.
And now we have our one language, right? So we basically need to be doing this to the inductive stuff, because we're trying to show that there exists some. This is just nonsense, right? We don't have this is notation for something, and we're showing that this is a valid notation. This interpretation still will end up being a regular language, right?
Yeah.
Mhm.
I'm trying to build that regular language right now, and that's what I'm doing with basically you really only need this rule, right? Because you can then take your induction and you say, look, I can just concatenate them all back together, and I can put them all under one parenthesis.
But then I think your R's, you need an R prime that contains the empty string for all of the ones after the first M minus 1.
An R prime that contains the empty string?
Or after.
What do you mean?
Right. Because you're going to concatenate together all these regular expressions. But if you concatenate n of them, so you have the maximum number,
Yes.
then you need n of them, but you want a regular expression that works for less than that many.
Right, and that is where this comes in. So I guess we
So
do
you need
this.
to union, or you need to,
You're right. So you need
or
concatenation
you could
and
define an R prime that contained the empty string, and you could concatenate the R prime if you wanted, which would be like those machines that we added that were optional.
Oh, that's another interesting way to do it. So you define.
And you could say that the R prime is equal to R because the empty string, but it's not actually.
Well,
Yeah,
you
so
can
that-
union it in, and that's still regular language. You need to
Oh,
use
that's
closure.
true.
You still
You're
need to
right.
use closure.
We're just trying to show it's regular, not that they're equal.
Right.
Yeah.
Yes. So if you want to build this new R prime that also includes the empty string to do what you're saying,
Mm-hmm.
then you'd have to union. You just define like L of R prime
Is
So
R union
is
empty
L
string
is
language?
L of R union with
L of
just like the set
epsilon.
empty string, right? It's
Yeah.
just empty.
Yeah. well, the language that
Yeah,
contains
L epsilon. You're right. Yeah.
L epsilon.
And that works. And then you're saying you put a bunch of.
That's why I used
Yeah.
that big union notation in the first place, because
I like
that
that.
that makes more sense to me than
Mhm.
trying to do an R prime and concatenating a bunch
I think
of
the
them.
R prime is going to be easier to do formally though.
Okay.
The union.
I don't get how the union does what that's doing. Or are you saying that they do different? They do the same thing?
So, the important thing is just that like you can't just concatenate LRs together, right? Because it's somewhere between m and n times, and so you can't like predict that ahead of time,
Okay.
like how many copies you'll need. But what you could do is you could do L of R m times, which is the minimum.
Yeah.
And then you add a bunch of like after you have LR m times.
Yeah.
Then you have L of R primes,
Which don't necessarily have to be included. That's why you have the empty string.
And you
Well, they have to be
define- you
included, but they
define
have
L-
an empty string,
Yeah,
so
okay.
you can basically.
L of R prime
Throw 'em out if you want to.
equals L of R, which is regular, concatenated
Which is
with L of epsilon.
no union
Union.
plus.
Yeah, that's not good. That's, my way's bad because it doesn't work.
What's really funny is I think we just solved exercise 6 as well.
Really? I didn't read it, so I have no idea. Another combination is a postfix operation. The preceding term is optional. Argue that adding question mark to the allowed regular expression is conservative. The simplest way to do this by showing is a regular expression equivalent to.
Like it's kind of relevant.
But I don't get why, like, I get the L to the M times, but
Yeah.
when you want to union more LR primes, how can you possibly get something that's like longer than LM R times or LR M times if you're unioning and you're not concatenating?
So you're concatenating the LR primes
Yeah.
in. You're defining LR prime using union.
Oh, you're concatenating them.
Yeah. You're gonna do this. What was it? Like m minus n times.
And minus.
N minus m
N
times.
minus m plus 1. Or-
no, because
Okay.
it's the same. It's different for this case than
Yeah,
when building
sorry.
machines, right? So this is just n minus m straight.
Concatenation.
Yeah.
Okay. But then why are we talking about the union thing in the top?
Oh,
So that was
this
a
is
different-
a way around doing that whole union thing at the top. You do need unions somewhere. You can hide them in here.
Okay.
Or you can do it that way, where you union together a bunch of different concatenated. You see what I'm saying? Like you do.
I guess I wasn't paying attention to what we were unioning, and that makes sense.
Now, does it make sense that you're unioning languages that are LR of various numbers of times?
Yes,
Yeah.
that makes perfect sense. I was
Okay.
just assuming that we were unioning LRs,
Which
made no sense to me.
And this is
So you're unioning
Unioning
every
LR would just
possible
give
length
you itself.
between K and an M.
but that looks good.
Okay.
This is probably the nicest way to do it. Do we see any flaws?
Well, now I like the top way a lot more.
Yeah. Your problem is like you gotta like do something inductive here,
Okay.
like some kind of inductive proof style thing, and I think this is basically that,
Okay.
right? Like this is like almost like a nice
It's like a
short way to
hack.
represent it. I think this is the best like short way to represent it, other than this. I like this, but like as far as proving this is regular, you really need to be getting down to these kinds of like atomic rules, like these rules he's talking about.
Okay.
Well, I mean, they're closed under union,
Yes.
and then each of those is a concatenate of a fixed number of
a finite times.
So you
Yeah.
can really make like
It's true.
you can make an argument.
I would probably still accept that actually.
Yeah,
It's
but
like,
aritra is like no,
Really?
no, I don't know. I'm kidding.
I think it depends. I think it depends how you say it. If you just put that and nothing else, you're done. But if you put like, notice that the distance between M and N is finite. So this is a union of some finite number of languages.
Right, and each of those has a
Then-
finite number of concatenates.
Exactly.
So
And then then we do like you show by induction, a finite number of concatenates is still regular. You still need
Right.
to do that.
I think you go in a circle. Like you have to do all of this. It just
Somehow.
you can just start at different points.
You don't have to do this. This proof would require you just to show the concatenation some fixed number of times is regular.
Right, which you
Yes.
can do with that.
Right, which
yeah.
you can do with just like a little more generic argument. You don't need these
I
R
think
primes.
can you not do it like an infinite number with a base case of one concatenate? Like
If you do infinite concatenation, you're just doing star.
okay.
Or is it? No, wait. Infinite concatenation is not star. You can't.
Well,
if
it
you
is.
do
It's
infinite
star over the alphabet language.
If you do infinite concatenation for like languages that don't have the empty, that can't be like simplified to something that isn't infinite, then DFAs aren't going to be able to decide that. They're going to run forever, right? Because they're going to need to find every
if
concatenation
the
point
inner languages are.
non-empty.
But infinite concatenation.
Like
Wait,
if you have a language that only if the only things in the language is the concatenation of infinitely many regular languages which don't have the empty string in them, then your language now only accepts infinitely long
So
strings.
then why does star work?
Star is concatenation some finite number of times, including possibly zero.
Star is finite. I
Star
thought-
is finite.
I was under the impression it could be infinite,
It can be any finite number,
which is all of them.
which is all of them, but it isn't like denoting that it accepts some infinite string. It's denoting that it accepts
So you
it and like strings of any number of concatenations of this some finite number of times.
okay. So an
Does
induction.
that make sense? That's
So an induction starting with like concatenating just two things, and then showing that if you can concatenate two, you can concatenate three,
Yeah.
and three
Yeah,
you
yeah,
can
yeah. It's
concatenate
just-
four.
you're just like, okay, well, base case, I do zero concatenations and it's regular. Done.
Mhm.
Inductive case, I have something regular and I concatenate something to it. Rule shows that this is regular. Done. It's like the easiest.
I feel
induction
like you
ever.
are proving you can do infinite, but again, it's just you're only considering finite numbers.
Yes, I'm
Right.
saying you can do it
Any
as
finite
many
number,
times as you want,
as long as
as long as it's finite.
right.
So like, star actually probably just gives you that that's true, I guess.
That's what I was originally saying. Like, if you want it to be very hand wavy, you could just say all of those L sub Ks are.
Don't do that. So you don't want to
I'm
say this is a bad way to do it. If I try and argue that this works because
Star
this is a
eats them.
subset of the star notation.
Well, we haven't defined subsets or that subsets are regular.
Sure. Well, it wouldn't be in this case, right? Because if I said if I want to say that all subsets of the star notation are regular, that's just blatantly false. Because think about it like this. There's a few ways to show this blatantly false. First, let's just say we're even in the unary language with just the symbol 1.
Mm.
Well, a subset of the star notation on 1, on our only alphabet character, would be
Oh, prime
all
number.
strings that are of length prime. Like
Right.
all strings of 1s
They're
that
in
have
the
prime
star.
length.
Yeah, they're in
Like
the
that's
star.
not regular.
Okay.
This DFA has no way to figure out if it's prime or not.
Yeah, that would be a big advance.
The other thing, the more major advance would be 0 union 1 star is regular. It accepts everything. And so if a subset of that were a regular language, that would mean every language is regular.
Okay.
See, do you see what I mean? Because the language that accepts everything is clearly
Yeah.
regular. You just make an accept state that goes back to itself.
Yeah.
that makes
So if a subset of a regular language was regular, then every possible language is regular, and that would actually, and that's contradicted.
And that would ruin the rest of this course.
We ruin everything. Well, we already know that certain languages are undecidable, and so that's already.
Okay.
And we there are proofs of things that aren't regular.
Okay.
That
So
things
the
aren't regular.
whole subset, is
Yeah.
a bad argument.
Subset doesn't work.
Exponentiation would be a better argument if we had like properly.
Just do the simple induction.
But
That's
yeah,
definitely
no,
the
I liked
takeaway here.
all the other stuff we did was
Okay,
much
cool.
better.
So like this is one way to do it. Another way to do it was like this argument, and you like don't rely on star because the induction is so short. Where it's just like base case, it's regular and it's by itself.
Yeah,
Inductive
right. This
stuff,
was like
yeah,
the
yeah.
simplest inductive proof.
And then you say right M and N, it's finite, so it's only some finite number of these union together, and then you have to do the induction again, saying that like some finite number of unions is still regular. You say a language by itself, it's regular, and then you say a language that's regular. From our inductive hypothesis, we have like n plus one of them now. The first n by our inductive hypothesis is a regular language. So then this union one other thing is regular by lecture. So you have to do an induction for this and this, I guess, because both of them have undetermined but finite unions. There's an undetermined but finite union and undetermined length but finite concatenation going
But
on.
if I do that, then I can skip the induction for union.
You could skip the induction for union, but you still do. I would say if you want to be careful, still do the induction for concatenation. Like, I don't know if they're gonna grade down for it yet. Like I said, I often do grading later.
No, I would definitely do this. This is so easy to.
It's so easy. I guess we probably will write down for it. I don't know.
You can say the same thing for union, pretty much.